from Indian Institute of Technology, Guwahati.
Seems some network problem with the madam. So we have from IIT Guwahati, Professor Hazarika. He works in the area of human-centric robots.
No, I'm sorry. I have the connection with some problem. I didn't get exactly what you said.
Yeah. So we have Professor Hazarika from Indian Institute of Technology, Guwahati. He works in the area of human-centric robotics. And he has especially joined for this course looking at your yesterday's presentation.
Okay, so you said that, I mean, I have some problem in my connection. I will log out and log in again, okay?
Okay. Okay.
Oh, I'm so sorry. I got disconnected again.
Yes, madam. Yeah.
Sitting at the heart of the Institute Computer Center, I keep getting disconnected. I'm putting my video off. I don't know what's the problem.
Yeah. So there was some problem at the Professor Domenico's end also. So he is again re-login.
Okay, fine. So good afternoon, all the participants. We hope that you enjoyed yesterday's session, and you have also got the video recording, YouTube links. You can go through them. And today we will be sharing the Google Drive link with you, where we will keep all the recorded not recorded material, the links to the recorded material and lecture slides. Thank you.
Yes, Professor.
Okay, let me test. Can you hear me?
Yes, we can hear you.
So please, can we start again what you said? Because now I think I have a better connection.
Okay, thank you. So we were just sharing the information that Professor Hazarika from IIT, Indian Institute of Technology, Guwahati, he had joined for this course, actually, especially based on your yesterday's talk.
Ah, nice. So
we welcome him also, Professor Hazarika.
Okay.
Hi, good evening, Professor Domenico.
Good evening, and nice to meet you in person, at least from remote. So you were with us yesterday, right?
I have been there with you intermittently yesterday, but today I have joined from my own room. Yesterday it was from my students together in the lab. So wonderful. From today I would do it on personally.
Okay. Okay.
Nice.
So thank you
for you, Professor Hazarika's main research interest is also in rehabilitation robotics and knowledge representation and reasoning. And so I'm sure that this is going to be a very good thing that he is present and will be definitely be enriched by his knowledge also. At the end of the program, we have requested him to tell about his research labs and research focus.
I would like
on
to
Saturday.
Attend,
sorry, you please.
I would like to be present when he will show his activity.
Sure.
When this will be?
Professor, on Saturday, we have kept a session along with their examination. So we will send you the updated information after talking to Dr. Hazarika.
Okay, so because of the presence of this expertise of this colleague, I would like to reorganize a little bit the lecture of today by deepening some aspect of the rehabilitation that I was touching yesterday. So the lecture of today will be some focus more on the part that I was discussing yesterday. So will be still a general talk, okay? Then I will have a focus on the mathematics of the manipulation, of the grasping, that is a bit more technical, okay? And then at the end of the lecture, let me just see if I can do something here with the audio. Automatic adjustment, auto, okay. Okay, should be okay. I mean, I have some noise reduction now. So then at the end of the lecture, a postdoc of my lab will present together with me a MATLAB toolbox, and then we will ask students, interested students, to do some exercise with us in the lecture, and then at home, if they are interested to do. So it will be more general at the beginning, some mathematical aspect. I will use a tablet to write the equation down, okay? And then a part on MATLAB, okay? And so I will start with the more general part. Give me 1 second.
Sure.
Because I was just reorganizing because of the presence of Professor Azarina. Sorry, what's the pronunciation of your last name?
Hazarika.
Hazarika. Okay. I mean,
So
I know.
Professor, he has attended your yesterday's lecture also.
Yes. I will complete part of the lecture of yesterday, because there are more things on rehabilitation to say, and I want to go there with my presentation. Okay.
Okay.
So basically, I'm still sharing the screen, no?
No, you haven't shared the screen yet. Yeah, now it is.
Now you can see, no?
Yes.
So yesterday we were talking about the sixth finger, no? But because of the presence, of you professors and colleagues, I would like to go a little bit deeper in this concept, no? And the concept, and I want to touch with you, is the concept of augmentation. Okay, what it means for augmentation. So augmentation means to make human enhanced, no, more powerful in some sense. So augmentation means to still stay in control of something, but being more able to do tasks, whatever it is. No, we have been used to use mobile phones, computers, smart bands, intelligence that we bring with you. So the phone is an additional brain that connect with my brain, okay, in some way, okay? Then, for example, my memory increases dramatically, so I can remember infinite pictures, images, because here I can store all the images. I can even talk in your language by talking in Italian, and the computer will automatically translate in your language. So this is something that we call cognitive augmentation, which means that we go for a normal cognitive ability, like in the head of this human, to something bigger, no? This is a larger brain that takes advantage of the human brain, of course, plus the augmented the augmented electronic brains that are in the computer and things like that. But if you look to these two pictures, this is really strange, right? You know, because you see a human with the same body of before, but a brain that is augmented. So what I want to say is that if we only care about cognitive augmentation, we will have probably a sort of bottleneck in the advancement of humans that is our body. So our body will probably represent a limitation of what we can do in terms of human enhancement if we only think about cognitive augmentation. So what I want to say is that over thousands of years, this is L'Uomo Vitruviano by Leonardo da Vinci, that dates back to 1490. And you see, Leonardo da Vinci actually is 60 kilometers far from Siena. So Siena and Florence are very close to each other, no? And in Italy. So you see so the legs, the anatomy of the body is exactly the same since thousands and thousands and hundreds of thousands of years. So what I want to say is that we, as technologists dealing with robotics, we need, in some sense, to think about augmentation of the body, not only augmentation of the cognitive capability. So we want to be able to become enhanced in terms of ability to do things. And in some sense, the extra finger I was presenting last lecture yesterday is a sort of augmentation. So is an extra finger, is something that we don't have before, but we can have with the human body augmentation, limb augmentation. So what we are talking about? So we are talking about basically now about another kind of intelligence, no? So we are not talking about cognitive intelligence, but we are talking about bodily intelligence. So there are many types of intelligence that goes from emotional intelligence, cognitive intelligence, ability to do mathematics, ability to do art. There is something related to the body. So something related to the body is, you know, maybe there is someone that has some very accurate skills in manipulating the fingers and doing some piece of art with their hands. There are people that are able to dance and they move they are very good in moving. This is bodily intelligence. So bodily intelligence is something that deals with the ability to move the body. So what we want to do in our research, in my research, is to augment the human body with the robotic technologies, okay, to have this body augmentation. So basically, I can deal with more limbs, okay, by keeping the control of everything. So I can have a task in the future. For example, think about this human with a wearable arm, okay, that is grounded on his body, okay, that allow to do 3 manual tasks. So there is a biological arm, a robotic arm that holds the same part, and there is the biological arm, the other biological arm that simply screws some part on the other, okay? Or in this other part, we are simulating a paretic limb, and the augmentation allow the human to move a tray very easily, okay? So for me, augmentation means to control some mechatronic device that is out of our body, okay? It can be either wearable or non-wearable, grounded, but it's something that I have the control of it. These are the kind of intelligence that has been defined in this paper in 1989. So is logical mathematical intelligence, linguistic intelligence, musical intelligence, spatial intelligence, body kinesthetic, that is the one I'm thinking to now, interpersonal intelligence, intrapersonal intelligence. No? So people that typically do AI think about something that is not related to the body, is something more related to the logical, mathematical, to the linguistic, to the interpersonal, so whatever, the intelligence, but not the one that we are pointing the attention to. Why? Because in my opinion, it's a little bit more difficult to deal with, because you have to deal with the data, plus you have to deal with body motion. So the mathematics that you need to interpret this kind of data is something that I want to stress, that we need knowledge on the sensory motor systems. Of course, if you think about the concept of, so what the augmentation is used for? Well, for sure, I'm Professor Azzarica, can you, I mean, it's okay up to here, to all of you?
Yes.
You are here. Okay. So what I want to tell about rehabilitation and augmentation. So for me, this concept is augmentation, but of course, we can have a healthy human here. Healthy human here is represented. So each edge of the shape represent a limb. So here we have 4 edges, which means 2 legs and 2 arms. So this is a healthy human. Maybe you can have an impaired human because of a paretic limb, okay, a paretic arm, for example. Then you can use the concept of augmentation that I'm talking about to bring the functions, the abilities to this human is dealing with to the level of healthy human. So I am adding a limb that is missing, okay? For example, in this case, I have a human that does not have a limb working because of the paresis. So there is a paretic limb here, and I can use an additional arm that helps him. You know, the big difference here, the big difference between augmentation and cooperation is that the robot is not completely autonomous. Of course, it's partially autonomous, but there is an interface that is the sensory motor interface that I was showing last time, either with ring or in case of the third arm. I had the Yeah, I presented it yesterday, a third arm, that they had the interface on the head. So the interface, the sensory motor interface, is crucial to make this collaboration more personal, okay? So there is a part of the control. I will give you an example right now in a moment. Let me go to this example here, okay? Suppose now that I am the human, right? I am the human with a paretic limb, okay? I am the human with a paretic limb. I cannot move this arm, now that is in my pocket, okay? Then here, there is a robot. Imagine to have the robot. Imagine that, sorry for the example. Imagine that this is the robot, right? And this is, I mean, imagine that this is a robot. You have to imagine something here. Then this robot is helping me, is like an additional arm, like in this case, that is helping me in doing something, okay? Then what I want to do is to have an interface, for example, a ring here or whatever, something on my shoulder that controls at least one parameter of the robot. For example, this robot can be, I don't know, 15 degrees of freedom, that is quite autonomous, okay? But for example, the distance from the end effector to my body is directly controlled by myself. So I still have a parameter of the task that is under my control. For example, the distance from the robot to myself, okay? So if, and this is for you that are working on intelligence in general. So in the robot, right, there are, let's say, 20 parameters, right? In general, not the joint, the 20 parameters are the parameters of the task that he wants to do. Maybe 18 parameters are controlled by the artificial intelligence, okay, inside the robot, but the remaining 2 of the task, maybe the distance from me as some rotation, is under my control. It's me that I'm controlling directly that robot with the interface. This increases 2 things. Gives me the agency of the robot. So I have the feeling that the robot is under my direct control, even if it's autonomous, okay, partially autonomous, okay, and makes me engaged in the process because I have to I have a paretic limb, no? So I have to use my biological arm to do something. The robot is helping me, so I have to control my arm plus the degrees of freedom in the robot that are under my control through the ring, through the sensory motor interface, okay? So the human is in charge of controlling his own biological limb plus controlling part of the robot. This is augmentation, it's not cooperation. Because cooperation means that the robot is completely autonomous. And then here, there, Professor Hazarika. Here it comes the fusion between the 2 intelligence. So here we are talking about mixing in some way the bodily intelligence, the sensory motor intelligence of the robot and the sensory robot intelligence of the human. So the robot should have some primitive that is partially controlled directly to the human. And this primitive of the robot should adapt to the human way of working. For example, if I have this system here helping me and a system, the same system helping Professor Kumar Gupta in India, okay? If there is a learning in the robot, at the very end, the primitive of the robot working with me under my control are different from the primitives of the robot that Professor Gupta is using, because the robot is adapting to the bodily intelligence of the human is working with. Is it clear? I mean, was it clear as how I explained this?
Yes, sir, it is. It is very clear, sir.
Yes, sir.
Okay. So this means that in this concept of extra finger, now, of course, the extra finger is maybe too simple to make all this intelligence, no? But in this extra finger, right? So the way the robot closes depends on how the human moves his limb. So here there is an intelligence that adapts over the days to what the human is doing. Okay, so if this robot has, I don't know, let's say 5 degrees of freedom, 5 parameters, maybe the human is controlling only 1. The other 4 are automatically adjusted with an intelligence that I call primitives of the motion that adapts to the human body. So we are really talking about, so the sensory motor interface in the light of the augmentation really try to mix the bodily intelligence of the human and the bodily intelligence of the robot. So we are quite successful in, and of course, here, the immediate application of this concept of augmentation is for impaired human, because for impaired human, it's simple, no? You don't have one arm, I will give you an additional arm that in my vision can be also grounded, not only wearable. Why not only wearable? Because, you know, wearable, wearing a robot, when the robot becomes an arm, you know, the human should bring with him the heaviness of the robot. Okay, so maybe I can imagine a human with a backpack. If I have a paretic limb, I can have a backpack. I take the robot in the backpack, and if I go to the office, I just dock the robot on the table, and I work with the robot as part of my body. And when I go in the kitchen of my house, I ground the robot on the kitchen plane, and it works with me. Okay, like for example, in a case like this. Like in a case like this. This is my LinkedIn. I want to see the activities. Oh, okay. So this is the project. This is the concept that I was showing. So maybe this is the most important thing. So this is the sensory motor interface. Okay, that is, and when he goes to the kitchen, he has both paretic arm. So he connects with this sensory motor interface to the robot, and he controls the motion of the robots and also perceive what's going on. So we basically go, in this case, we basically go from 3 or less than 4 limbs to 4 limbs again, okay? And this is also actually to be, I really like the story behind the logo of this project, because this is a human, H is a human, the triangle stays for A, that is a person with impairment, that thanks to the robotics and the interface, the limbs, becomes with a square again, with the 4 limbs again, even if one is artificial, okay? So going for less limb to more limbs integrated with body is the concept of augmentation that we have. So there is a story behind the logo of the project. Of course, we can also think in the future about augmentation for healthy human, because I always think that if I don't know if you professors agree that as a scientist, if we want to develop, if we want to help people, we need to develop technology for healthy people. For example, this tablet, whatever tablet it is, okay, is designed for healthy subject. No, I will use it in a moment to do the lecture, but it's typically used from people that cannot see very well, not blind, but poor ability of seeing. So they attend the conferences, for example, by zooming a lot on the tablet and looking what's going on the remote screen. Now, this technology is very good for almost blind people, just because we are using it, just because the market is huge for healthy people. Okay, and then the performance, so they sell more, the performance goes up, and the cost of the device goes down. So any project I have, I always try to find a corresponding, even if I want to improve the quality of the person, I want also to find an application for healthy people that increases the number of people that are interested in, and for certainly improves the technology for people with impairment. And there is also a concept of inclusion, of course, because if I use the same technology, if I cannot see very well, and if I use this technology that some friend of mine is using the same technology for other things, I feel more, more comfortable in terms of inclusion. No, it is a big concept. Okay, so we are basically talking about the fusion of the human intelligence and the artificial intelligence of a robot through a sensory motor connection. We have been working a lot on this project. So we have, yesterday I did not present the results in terms of rehabilitation, but we did many tests. We published tests on the franchise arm test. For example, people with impairments without the extra finger were only able to stabilize the ruler, a ruler. They were not able to grasp a cylinder. They were not able to pick up a glass. And this was possible with the robotic extra finger. We already saw this yesterday. I will not skip it. It's really the concept of the big concept that I'm presenting here is the main difference between cooperation and augmentation. So the old story of the cooperation is that you have a human with human limbs, you have a robot that is completely autonomous, and you do a cooperative manipulation task. In augmentation, you have an interface that connects the human to the robot, so the human takes the control of a part of the robot and do the task in an augmentative shape. Okay, so in some sense, the additional part of the sensory motor interface makes the augmentation possible. Is it clear, this concept? The big difference between the cooperation and augmentation? Can I have some comment from you? I think so. I think that
yes, sir, clear.
Yes?
Clear, sir.
Yes. So the big difference between the cooperation and augmentation, so cooperation, it means that human does not control the robot at all, okay? And both of them do the task. So if the finger was completely autonomous, without any ring interface, without any sensory motor interface, this was just a cooperation, pure cooperation. If you add the ring that controls in some way the robot and feels the robot, so I can control the robot and feel the robot, then this is augmentation, okay? Because I feel augmented with this robot. That is, for me, is really, you know, the interest that I have for augmentation is impressive. Because I think that there are many open problems for people doing AI, because we are talking about mixing the two intelligence, the two bodily intelligence. I have a question here, maybe. Okay, the concept is clear. Thanks a lot. Now, just to take some, before going to the lecture on grasping, let me see if I want to show you something that was not discussed yesterday. This is another example of sensory motor interface. This is also very, very interesting, right? Because you have a human, a lady that has an impaired arm, and she wants to use the biological arm, the remaining biological arm, both to do the task with the robot, like pouring the water, but she wants to have an interface that directly controls the robot, to feel the robot as an extension of her body. And she's using a part of the body that is not involved in the task. Now the question is, suppose that she can walk. So should she use the shoulder or maybe a leg? Because I can connect the sensory motor interface almost everywhere on the body, okay? And what I want to say is that we don't, for sure, I cannot connect the interface directly to the hand that is healthy. Otherwise, you know, I don't use the health anymore. I mean, I can make busy the part that she's using a lot. No? So this is the concept of null space, so that we use the degrees of freedom that we typically don't use in our biological task. But I will go in a moment there. The interface can be of 3 types, and we are working on that. So the interface, that is the very important part of the story. The interface here, this is the interface. Recognize an action of the human that becomes the reference for the controller of the actuation of the robot. Okay, the robot has sensors on it, okay, that are feedback on the perception system of the human. Example here, the human pushes this switch, okay, so is the action. This is recognized by the electronics here and starts the motion of the robot, okay? So this action is connected to the robot actuation, okay? The robot has a force sensor here, okay? This force sensor measures the interaction with the object, so senses the force that is feedback that has been provided back as a stimulus on the human body by squeezing the finger through this cable. So there are motors that are connected to this sensor that stimulate the finger, okay? So the action is recognized, is translated in a motor activation. The sensor measures something, provides a feedback through another motor on the human body that provides the haptic feedback, okay? So this is the, I mean, for me, this is the most interesting part of the human augmentation. Okay, so this kind of action can be a voluntary action, like squeezing a switch, can be a voluntary motion of the shoulder or of some other part of the body that I don't use, but can also be done at 3 levels, another level. So it can be, you know, kinematic motion of the shoulder or whatever, but can also be a co-contraction of the muscle. So now I can hold the glass with my hand, but I can co-contract the muscle of my arm, no? And they can, or the shoulder. And I can use this co-contraction to control the supernumerary limb, okay? So I can find in some way the control of the sensory motor interface, not only in the motion, but only in the muscular activation. And in the future, if I have a nice interface of the brain, I can also try to find some null space in the brain. All these aspects are discussed in the Nature Machine Intelligence paper. This is, for example, a kinematic intrinsic null space control of the end motion. I can show you, maybe I can show you directly. We did a lot of experiment, but I will show you the experiment that this student was exaggerating the motion of the shoulder. But you can see now, this is very important. Follow me, because this is very, is a problem that is really mixing the science with the art and with even the dance. Look, so Tommaso here is controlling, is simulating a paretic limb. So he's simulating that he does not have this arm, right? Because it's paretic. So he can, I'm sorry, as a paretic hand, not arm. So he cannot, he cannot grasp the object normally, no? So he needs an extra finger, okay? But this is not cooperation. The extra finger is not autonomous, completely autonomous. And the shoulder is taking the control of the finger. So the finger, the robotic finger, is augmented with an interface on the shoulder, okay? The shoulder is measured by using a Vicon system, body tracking system. Look, he is doing, the motion of the shoulder is associated to the motion of the finger. I don't know if you can see it. Is it clear what's going on?
Yes, Professor.
Okay. Now, if you look to this motion, the way we control the shoulder, the way we connect, the shoulder to the closure of the finger, you know, it's us, it's the algorithm. We design it. No, I can say, look, if I move the shoulder like this, I mean this one, if I move the shoulder, close the finger, no? So I can do this kind of action. But what about the elegance of this motion? Is it more elegant, this, or maybe this one, because of the symmetry? Is it more elegant, this, or maybe the motion of the elbow? So how we choose the motion of the body, of the human body, to control the supernumerary limbs? It's a matter of, you know, accepting the motion. So it can be some motion that is more, that is more beautiful than other. But what beautiful means? How do we measure sort of, can we measure the, you know, the symmetry? Is symmetry a concept of nice motion? For sure, we need to connect the motion to the ergonomy, no, of the human body. So we need in some way to understand what are the more natural motion of the thing. And now I am really going into the connection. So if you look, so what this kind of discussion remembers you? Don't you have in your brain something, someone dancing? So if you go to see a ballet in a theater, it's the motion of the dancer, something that we like to see. Is there the elegance of the motion? Should we also look to the trajectory of the human body while dancing? Is that a way to interpret and connect the motion of the human body to the extra robots? And I'm really, so any time my research goes in the direction of humans, I simply trigger, so something triggers in my brain and I get more energy. I don't know why. So I'm in love with the research of this professor here. And I don't know if you are aware of her. So she's something that I really would like to mention.
Apri il tuo negozio online e vendi i tuoi prodotti su Facebook e Instagram con Shopify, la piattaforma di e-commerce scelta da oltre 1 milione di attività in tutto il mondo.
She's Merit Moore. She's a physicist that dance with robots. I think she's doing this offline. So she coded the robot in order to have the dance with the robot together. No, she really coded the robot. No, she's the engineer behind. She's a physicist actually. She's a very nice person. I suggest you to follow her research. So basically, what I want to say is that there is a nice thing between connecting the human body to a robot that can inspire me, my research, my group, to find very beautiful body motion to be used in the concept of augmentation through the interfaces. So she's not using the interface. But this is, for example, an example of body intelligence augmentation for healthy subjects, okay? So she's augmenting herself like if she has another limb, another body that is deeply connected with her, okay? Now, what we are doing here, and this is a very nice research that I want to even involve someone of you if he wants to, if she or he wants to come to work with us here, or even collaborate, as I told you. And this is again an invitation to find a way of collaborating. So what I'm doing right now, and this is the first thing that the first time that I show this research in the world, I mean in the online. I think that we are online on YouTube. And let me just give me 1 second. I'm going to catch a movie that is on my desktop. Where is desktop? Oh, here, P, desktop. Then I have the list. Then I mean too many things on the desktop. Sorry for that. It's not very elegant. But this is a dancer. It's a little bit more, you know, there is some emotional part here because the dancer is my daughter. So she's my daughter, Elena, 11 years old. And she learned, she liked to move herself. And she learned to move this Korean pop dance alone. Okay, so she's not perfect, but very interesting, 11 years old. And I put the body tracker on her. This is a room of a classroom in here in Siena. This is me and my students. You will work with in case we want to cooperate. And this is I put the body tracker on her body with the accelerometer. Okay, so she has immediately a digital avatar in the screen. Okay, so I can track her motion online. Then I will take the principal component of her motion and I will connect in the next step of this research her motion online with an arm, with a robot. Okay, that is this concept of augmentation. And the dancer is something we need to look at anytime because they are using their body completely. So me, Professor Gupta, Professor Aparajita, Professor Hazarika, and we use our body not in the full, their full ability, because it's not a dance, it's not a sport. You know, we write, we type, we walk. Dancer and typically people doing sport are using their body completely. So there we can find the richness of the motion. So because we need richer motion to connect this additional motion to the supernumerary limbs and become augmented humans. So we need to become a little bit more dancers, okay? And to connect part of our body that were not moving before to the supernumerary limbs. That can be even domotics, okay? So we serve a couple of objectives. One is to move the additional limbs, and the other one is to improve the motion of our body, because we are going to the gym to exercise ourselves. But with this sensory motor interface, we can do something more intelligent and do more things by moving more our body. Look. This was me. Look, the avatar that is moving, of course, online. There. So what I want to say, look to this concept, because this concept is completely new in my opinion. So, and now I'm talking about Elena, but I will never think about her with any kind of impairment. But imagine her when she becomes, I don't know, 80 years old. Then maybe she has some stroke, some part of the body is not working anymore properly, but she's a dancer. She has additional degrees of freedom. Very useful to be connected to the extra limb. So she will have the control of her body so powerful that we can connect with sensory motor interface any part of the body that remains able after the stroke, and we can augment with that part the number of limbs she can control. So for me, dancing or doing sport, if we are able to do this research deeply, will be the real thing that we can do for our body to be partially save some function in the future. So if I'm a dancer and if I have a stroke to one arm, I have the whole body that I can control very well, and I can control. Of course, if I can move this part of the body, it's completely unuseful, okay, for doing things in the kitchen. But if I connect my sensory motor interface, and if I am able to control an arm with the body motion, because I was the dancer, then I will get the supernumerary limbs as part of my body connected to another part of my body. Okay, is it clear, the concept? Can we have a little discussion here with my colleagues?
Yes, sir.
So what do you think about these ideas?
These are very interesting ideas.
Really?
So there are a lot of options of controlling the devices through sensory motor interface. For example, we can take EMG signals, we can take EEG signals.
Yeah, there are many options. For example, right now in my lab, we are designing an interface that takes both the motion and the EMG. So even combining this signal is important. Then when I take, for example, one thing that I'm really interested in is if we take the EMG, maybe I get a little bit more tired after a while. So maybe using the body motion is more natural, no?
So
by the way,
is there any trade-off between EMG and the force signals that you are talking about?
Trade-off, say again, trade-off?
Is there any trade-off between the EMG signals and the force signals that you are talking about?
So there is always a trade-off. Yes, I know we are studying it, but this is a new research trend in my research group, and I think that this goes back to what I was saying yesterday with Professor Aparajita and the other colleagues I was talking about. So there is something that really goes beyond pure robotics, beyond pure engineering, beyond pure AI. So here we are talking about involving people that are in a theater, doing ballet, dancing. So really, I think that we need to think about research from a very different perspective, First, we need to be competitive with the huge companies like Amazon, Facebook, Apple, Google. They have not 20 students like me. They have 100 skilled engineers doing research. Okay, so it's a very well organized stuff. So as professors, I think that we need to redesign worldwide the academia in order to be more integrated, because I cannot become an expert of dance. I cannot become an expert of EMG. I got the idea of augmentation. That is probably one of the things that I'm really going to push a lot in the next years. And but I need expertise. But to have the expertise involved, what we need to do as professor is to inspire the colleagues. Because if a colleague is not inspired, she or he will never work with you, no? Because she or he has to feel the project as if the project is her project, is his project, okay? So we cannot go around and say, this is my project, you want to collaborate with me. So the way I come with you, I go to you is, this is a rough idea. Would you like to build a more defined idea together? So you feel the idea as part of your lab, and I feel the idea part of my lab. In that way, we can really put the energy together and make something happen. And this cannot happen in the same university, in the same country, maybe in the same area. This should happen worldwide, because we need really to change the concept we do research, in my opinion. And this GIAN project goes in this direction. Because before you need to attract, to tell what you do, attract the interest, and then you can build the path together with the colleagues interested. I have to say that it's a little bit more interesting to engage the scientists and the professors than the students, because the students come here, become a PhD of mine, is wonderful, is perfect, is what I like to have in the next 2, 3, 4 years. But if I have a collaboration with the lab, so with another professor, with her or his lab, and we become a unique meta lab around an idea, is much more powerful. So I get more energy in the common path than a single skilled PhD. That is what we are looking for, and I am also looking for. But in the long term, I think that we need to change the way we do research worldwide. Okay, good. Going to, I mean, this is the inspirational part of the work. And I think that we can take 5 minutes rest, and we can go to the more technical part. Hmm?
Okay.
Do you agree?
Yeah, I think, Professor, we can have 5 minutes break.
Are there questions? I mean, can I have some comment from you about the model of doing research?
If anyone wishes to share something, any participant?
Hello, sir.
Yeah,
Yes.
So I have singled out. So which type of sensors you were using for that augmented reality in which the dancing was happening? Your daughter was dancing and
Yes, it was a IMU.
only IMU?
IMU, only
Nothing.
IMU, and it was of course, there was a model behind of the
Okay, so
human body.
EMG was not involved in that?
Second,
EMG sensors were not involved.
no, accelerometer, magnetometer, inertial
Okay,
measurement unit.
Okay, sir.
No
Thank you.
vision, no computer vision.
Okay, thank you, sir.
Okay.
Sir, I guess it was basically the motion of the limb that was being tracked, right? For
Was
right,
the
sir?
motion of the limb.
Yes. Sir, does this implicate how much, like, say, with the motion of the limb, if we're trying to grasp a object, so will that define that how much force that needs to be applied there through the motion? Like how high you need to raise your limb for that to increase the motion of to increase the force of grasp.
So you mean if we can get the force from the motion?
Yes, sir.
You can do it, but only if the object is deformable. So, for example, on a rigid object, you don't have any idea about the force that I'm applying, right?
Yes.
If I have a deformable object like this glass, from the motion, you can get an idea of how I'm squeezing it. Okay, so for rigid object, you cannot get any idea about the force. So you need force sensors like we were using on the extra finger.
Yes.
Okay, good. So talk to you in 5 minutes.
Okay, Professor.
Okay, bye-bye. Okay, I'm here again. I don't know if the 5 minutes went.
Yes.
Okay, so we can start again.
Yes, yes, sure.
Okay, so it's now it's really more technical, and so it's I will write something and I will show to you something about it. Okay, so the main so when we were talking about intelligence, when we were talking about yes, intelligence and yes, okay. So when we were talking about intelligence, bodily intelligence, biological limbs, robotic limbs, doing tasks together, 3 arms together. Remember, still, I mean, I think that I need to share my screen, right? Yes. So we were talking about something like this. This, for example, okay? Take this example. So there are 1 hand, 2 hands, 3 hands working on the same object, okay? So the mathematics behind this complex manipulation, that is probably the most advanced action of the of the bodily kinesthetic intelligence, so means to cooperatively operate with a single object. So if you abstract this concept to a more general level, okay, we are talking about grasping, manipulation of an object, okay? So the things that these 3 fingers are doing to this object, for example, my pocket here, okay, these 3 fingers are doing to my pocket is the same mathematics of these 3 limbs acting on the same object, okay? And is the same mathematics of these many robots working in the Tesla industry, manipulating the chassis of the car, okay? For example, in this case, I am squeezing my pocket, okay, without moving the body center of the pocket. This is called internal force, okay? So this means squeezing the object without moving the position of equilibrium of the object, but I'm squeezing it. At the same time, these 2 robots that are operating on the left and on the right should apply a level of forces that do not move the chassis of the car, neither on the left nor in the right. So they have to operate by squeezing the, like squeezing, they are not squeezing actually, like squeezing the car. So they have to manipulate the object. So at the very end, everything is similar to the mathematics behind the robotic gripper or robotic hand. That is the subject of the talk of the next of this part of the lecture. So we will talk about robotic manipulation, but we are talking about many robots collaborating on the same car. We are talking about humans and robots in an augmented fashion. is exactly the same mathematics, okay? But because traditionally we were working on robotic hands, the mathematics, the model behind is represented onto robotic hands, okay? Most of the work that I'm going to present is published in this, I don't know if you can see here. This is the robotics handbook by Springer. I don't know if you know it. The people that are doing robotics probably knows. It's the Springer handbook of robotics. I have a chapter in that book, and the book, the chapter is called Grasping. Is the book I'm talking about is Robotics Handbook Springer. This is the book I'm talking about, and I wrote for this handbook a very detailed chapter on the arguments that I'm going to touch today. Of course, I will touch some important part of the book. You see here, I think, you know, so these are the chapters. I'm looking to the to my chapter. This is my chapter, Grasping, that I wrote with Jeff Trinkle, a colleague from US. And here you can find, so this chapter introduced fundamental models of grasp analysis. So there is no technology here. It's only math. And you can have a look to it in case you want to have more information about it. All this mathematics is also reported in this other course that I teach, is the art of manipulation and grasping. That is a course online where you can find the video lecture that are much more detailed than, I mean, this is a course, so on grasping. The course that I'm teaching here in GIAN is more general. Grasping is a part of it. But if you want to have more knowledge about the mathematical model, you can have a look to it. There are some notes that I will show you today, but actually I will probably sketch it on the tablet. And more interestingly, there is a toolbox here, free toolbox based on MATLAB that Dr. Maria Pozzi will present at noon 30. Okay, sorry, in 40 minutes, more or less. Okay, and this SynGrasp toolbox you can install, and you can use the functions to build your hands and whatever. Okay, there is a human hand that we also use for avatars in virtual reality of the hands. So there are human hands and robotic hands inside. Okay, but now in these few minutes, I will try to give you the core concept of grasping. Okay. Yesterday I had a nice student talking with me. I don't know if he's still here. We can keep talking about together grasping. I'm looking for an object to manipulate, and I will take this object here. Okay, so what's grasping? Maybe I don't need I will stop sharing the screen because I think that my face is important in this part. Well, so what's grasping? So what do you want to do with the, no, this is black. I will take a white one, just a sec. If this is an object, what do you want to do with an object? Actually, we want to control, again, the motion of the object. In the pen, I want to write, I want to make a signature, I want to control the motion of the object. So this object per se, if you take the object, if you take the object on a table, right? The object has no motion at all. Okay, means no actuation, not at all. So what do you want to do? So of course, as an inertia, as a mass, as a dynamics. So if it falls down with a certain dynamics, but has no internal motion. It's not a robot. It's not a pen writing itself. So you need to transmit the motion, the forces onto the object through your hand and through your robot. I mean, this is a robot, no? But it can also be, so the same mathematics is behind the human hand and the human arm. So either flesh and bones or metal and wires, the mathematics is the same because obey to the physics. Well, you want to impose a certain motion to the object. So you want to apply certain force to the object. For example, the first force that I'm simply applying to the object is a force that is opposite to the gravity, because there is a gravity force that is sending the pen down, and my hand is applying a force that is opposite and equal to the gravity force. Correct? Okay. How I apply a force to an object? The way I apply a force to an object is through contacts. Okay? So I'm applying forces to the object through these three contacts, 1, 2, and 3. So the main element of a grasp are the object, for sure, you want to manipulate, the contacts that are the physical interaction by means of which you transmit the forces to the object, and at the contacts, you have your fingers, okay? The robotic fingers, of course, that are controlled to do some motion, okay? Now, the object here can move in two ways. The first thing is called power grasp, which means that, I mean, look to the motion of the hand, right? There is a motion with respect to the palm, no? So with respect, I keep the wrist still and I move the finger with respect to the palm. This is called dexterous manipulation. So if you move an object, if you are able to move an object with respect to the palm, this is called dexterous manipulation, okay? If I move the object, because I'm moving the wrist like this, so the finger are not moving with respect to the palm, but only the wrist is moving because of the arm, this is just manipulation, it's not dexterous, okay? Are you with me?
Yes, sir.
Yes.
Yes, sir.
Okay, perfect. Of course, you can imagine that the dexterous manipulation is the very interesting one, right? Because if you want to move the wrist, we typically use something that is called power grasp. You simply take the object, you lock the object in the hand, and then you move the wrist. This is called power grasp, okay? The power grasp is where you don't care about the in-hand motion. This motion is called in-hand, which means with respect to the palm, okay? In-hand motion, right? In this case, you don't have too much in hand motion, okay? Because you are caging the object. So what I want to say, if you have a robot, right? And if you want to move an object around without any dexterity, simply realize a power grasp and trust the motion of the wrist. This is the simplest thing, right? Ensure the grasp, like gluing it with the glue, okay? And then move the wrist, okay? Once you cage the object, it's the simplest way to do. So if you have to move things around, that's okay. If you want to do in-hand manipulation, in-hand dexterous manipulation, which means moving, like a surgical tool, moving a pen. Even, for example, in this case, no, when I am, when I try to screw the to put the cap on the bottle. This is dexterous, no, because I'm moving with respect. I'm not doing this. I mean, I can also do this. This is power grasp, not dexterous. This is dexterous, no. So there are many things that we do with our hand that are dexterous manipulation, more advanced manipulation. Okay. By the way, the mathematics for doing power grasp or dexterous manipulation is the same. What are the objects of the manipulation? The object of manipulation is an object, okay? The main element is an object, the contacts, okay? And the hand through the contacts. The only thing that you have to take care of is how you transmit the forces from your robot, especially, I mean, right now, consider with respect to the palm, okay? Consider this from palm on. So you want to apply a certain kind of forces to the motion and then forces to the object, because you need to move the object. But the motion of the object has a certain dynamics, like mass times acceleration, inertia times angular acceleration, and then all the internal torque, some other forces, but basically there is the inertia, and then you have the applied forces and torques. So you act, mass acceleration is equal to force, you apply a force, and the physics integrates the system, and from the acceleration goes to the motion, okay? This is simple, physics or second order differential equations that you apply the force to it. Simple physics, okay? The only thing that you have to take care of is to understand what kind of force you want to apply to the object and how to transmit the forces through the contacts, okay? And how to control the joint of the forces, okay? You have also to take care about something else. You have to take care that the contacts hold true. So these contacts are constraints to the forces. I don't know if there are people doing mechanics or mechanical engineering or physics or whatever, even electrical engineers should know this, but a force can be applied without moving the contact point only if the force is in the friction cone. So each contact has a friction cone that depends on the material. And if the force is directed in the friction cone, then the contact does not slip. Otherwise, you have slippage. Okay? Good. Now, if I can, do you have a question here?
No, sir, it's fine, sir.
Okay. Now I need to take some notes, and I will share my tablet. You see it, right? The tablet. No, because I'm not sharing the screen. Let me share the screen. I think that now you see the screen of the tablet.
Yes.
But also you see my face, no? I need both. You see me? Can you see me, the hand?
Yes.
Okay, so in the grasp or grasping, the main element are object. You want to manipulate. Okay, this is the object, like this small square. The contacts, like in this case, you have three contacts, one here, and one here, and the robotic hand. Finger, and hand. Okay, so these three elements, the contacts, the object, and so the fingers are here. I mean, let's take you have one finger here. Imagine to put this is a link, this is a joint, this is a link, this is a joint, this is a link, this is a joint, this is a link, this is a link, this is a joint, 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 and here you can find the palm, right? All these fingers are grounded to the palm, okay? Do you agree with me? So you have three fingers, like these three fingers. These fingers has 1, 2, 3, 4 joints. Okay. This other finger has, I mean, these are robotic fingers. This other finger has 1, 2 joints. Okay. And this other finger has 1, 2, 3 joints, and all of them are attached to a palm. Okay. So this is the palm. I will simply ground it somewhere. Okay. Now, what do you want to do? In this copy, I'm going to take okay, so what do you want to do? I'm just writing it down. If this is the object, no? For example, the object is subject to a gravity, no? And this gravity, okay. Now, for simplicity, I'm removing the torques for some reason, okay? But the more general aspect will be detailed in the book, okay, in the chapter, or in the lecture, video lecture that are free. Okay, so if you have the gravity, which means a vector that is equal, for example, if this is the reference frame that is x, it is like x, y, and z coming out of the box, okay, then gravity means like 0 along x minus mass times gravity along y, okay, and 0 along the Z. So this is the force that is applied by the external sources, right? What you want to do with your grasp is to apply a force that is equal and opposite, okay? You see now on my hand, there is the gravity going down, and with your fingers, you want to apply an opposite force that compensates for the gravity, okay? So this is your action that you want to do. And this action should be done through the contact forces, okay? Now, I call it, this is external branch or external force. No, I'm talking about, this is a force, okay? But indeed, there is also the moment around X and Y and Z. So in general, the external branch would be like 0 minus mg, 0, and then 0, 0, 0, because it's not rotating in this case, okay? But we can, for simplicity, I need to skip this part and just considering the external force, okay? So just for a moment, just remove the torques and moment. So what you want to do, you want to apply a controlled force, F controlled, because it's under your control, that is equal and opposite to Fx. So you want that your F controlled plus F external is equal to 0, because you have equilibrium, okay? It's not moving. If you want to move, this is not 0, but at least now pick it not moving. Now you need, so what do you want to do in terms of control? In terms of control, you have a box and you want to apply this force that you know it, okay? This is something that you know, right? And you want to do it by these contacts, okay? At these 3 contacts, right? Like in this case, you can apply forces, okay? So then I call it contact 1, contact 2, contact 3, and I can apply really with robot, I can apply a force at contact 1, at contact 2, at contact 3. So you have FC1, FC2, and FC3. That are the forces that you can control with your finger, okay? Are you with me? The only thing that you have to be careful, if you zoom at this contact here, if you zoom at this contact here, you can, so you have that this is contact 1, you can apply forces only in the friction cone. So only if you apply forces inside this friction cone, you don't slip. So the contact does not change at all, okay? So this FC1, FC2, and FC3 should be controlled to satisfy the contact constraints, okay? Must satisfy, in order to be applied, the contact constraint, okay? There is a very important matrix here that depends only on the position of the contact, okay? That is called grasp matrix. Matrix is the queen of the matrices in grasping, even in collaboration through contacts. So the grasp matrix is a matrix G that depends on the contact C1, C2, and C3, C4, C5. I mean, this is generalized. If I have 5 contacts, I have 5 contacts, right? Is a linear map from the contact forces to the control force. So you have that the controlled force, the red one that you can control, is equal to G Grass matrix times FC1, FC2, FC3. What's the dimension in this case? This is a three-dimensional vector. This is a three-dimensional vector. This is a three-dimensional vector. So this is a 9 by 1 vector, right? You put one on top of the other. So this matrix has for sure 9 columns, okay? Because they have to multiply the vector. How many rows it has? As the forces, actually, it has also the controlled moment that is 0. This is the external, the branch control that is part of the force and part of the moment. For example, in this case, I'm also controlling a moment because it's rotating, okay? So I'm controlling the net force on the barycenter of the object plus the net moment on the barycenter of the object. So this is 3 forces and 3 moments, okay, about the axis X, Y, and Z. So this is external branch that takes, is equal FC MC, and this is 6 by 1. So this matrix is 6 by, has 6 rows. So G belongs to real 6 by 9 matrix. Okay, right? So given in a grasp control problem, you have FC is given, sorry, WC is given. No? If this is the object, this is the gravity, you want to compensate, so WC is equal 0, mg, 0, 0, 0, 0. This is what you want to do, right? Given WC, given the grass matrix that is very easy to compute, just have a look to the book. You want to compute FC1, FC2, and FC3, right? So this is known. This is known. This is the unknown, right? You want to, the robot needs to know which forces should apply with the fingers in order to resist to the external branch, okay? So you need to solve this linear system, okay? So that is FC1, FC2, FC3 is equal, please remember the solution of the linear system is equal G pseudo inverse times WC, that is given, this is given, plus, do you remember, here you have in this equation, how many equations you have here? You have 6 equations, right? Because these are 6 in 9 variables. 6 equations in 9 variables. It means that you have infinite solution, right? Because you have 9 variables for 6 equations. You can find infinite solution. So this infinite solution is represented by the null space plus the null space of G, the base matrix of the null space, times zeta, that is the parameter 3 by 1 that represents the domain of the null space. So the fact that you have infinite solution is super important, is the most important thing in grasping, because you can find among all the solutions the one that satisfies the contact constraints. So the force that you find should satisfy the contact constraints. So among all the infinite solutions for these forces, you can find the one that satisfies the contact constraints, right? So you take from the infinite solutions for FC1, FC2, and FC3, you take the one satisfying friction constraints. In the sense that you want to, if this is the block, if you want to resist this force, okay, for sure there is you have these three contacts, 1, 2, and 3. For sure there is this combination, 1 and 2 and 3, such that the sum of this, and this is equal to this, right? This is a possible solution. This is the barycenter, okay? This is the gravity. Is a solution? No, because you have to stay in the friction cone, and only this one is in the friction cone, okay? So this is a solution, but it's not a solution that solves the problem. You need to find another solution that I'm just showing. Among the infinite solution, you have to find probably this one, 1, 2, and this is larger, okay, that compensate the sum of these three forces, 1, 2, and 3, generate the exact opposite to this. So this should be, of course, line. Okay. Then you can have, and this is the, this red one is the one that you find among the infinite solution. Is it clear, the concept? I don't want you to go into this detail, but the concept is clear. The infinite solutions for the forces is the ones that you need to satisfy the constraints on the contact force. Once you find the forces at the object, okay? Once you find the forces at the object, so at the very end, you find this solution, right? 1, 2, and I don't know, maybe we said this one, like FC1, FC2, and FC3. You need to apply with your torque. I don't know if you are familiar, but if you have a kinematic chain, like a finger, like this, right? And you want to apply a force here, Fc, the relationship between the torques that you apply at your joint, at the motor joint of the robot, is this one. If you call this tau 1, tau 2, and tau 3, the torques are proportional to the current to the DC motor in the joint. So the relationship is tau 1, tau 2, tau 3 is equal the Jacobian transpose, another big map of the Jacobian transpose times Fc in this case. So given Fc that you get from the previous equation, you solve, you multiply by the Jacobian transpose, and you get the torques that you need to apply to the finger, okay? You do this for all the fingers. So in this case, you have for this robot, you have the decide force that you want to apply, okay? Then you have the Jacobian of finger 1, the Jacobian transpose of finger 1, Jacobian transpose of finger 2, Jacobian transpose of finger 3. You have F1, FC1, FC3, FC2, and you compute the torques that you need to apply. So you have tau finger 1 is equal Jacobian transpose finger 1 times force contact 1, and then the other finger. There is we call it Jacobian of the end. The Jacobian of the end is something that takes everything together. So the Jacobian of the end is that if you have the overall torque of the hand, in this case from tau 1 to tau I think it was tau 9, all the torques of the finger, is equal Jacobian of the end transpose times FC1, FC2, and FC3. And this JHT is simply done by J finger 1 transpose 0, 0, 0. J finger 2 transpose 0, 0, 0. J finger 3 transpose. Okay. By the way, summarizing before giving the voice and the stage to Maria Pozzi. I don't know if Maria is here. Maria, are you here?
Yes.
No. Okay. Ciao, Maria. So to summarize, the core of the contact of the grasping control is that you have an object. You have an applied wrench from gravity, for example. You want to apply a controlled wrench here, VC, that is equal and opposite to the external wrench. Okay. Given VC, you solve with this equation, with grasp matrix, you find FC1, FC2, and FC3. And the grasp matrix is a function of contacts, C1, C2, and C3, right? So given the contacts, right, you find, solving this equation, okay, you find the contact forces that you need to apply, okay? You have infinite solution, I explained before. You use this infinity to satisfy the contact constraints. So from VC, you compute FC1, FC2, FC3 with the linear algebra, okay? From FC1, FC2, and FC3, you multiply by the Jacobian hand transpose, and you get the torques that you need to apply to the joints, okay? The two main equations are VC is equal G FC, where FC takes all the three contact forces together, and the other one is tau that you want to control at all the joints is equal the Jacobian of the end transpose times FC. So given VC, that is a function of the external branch, from this equation you compute the contact forces, and from the contact forces, by multiplying by this other matrix, you find the torque that you need to apply to the joints. And the torques are proportional to the current. Yes, Professor. Aparajita, you are muted. Ah, no, she's not talking with me. Okay, good. Do you have questions here? Professor Aparajita, you are talking with me? No.
No, I'm not talking. I was just waiting for some questions. No questions from my side, Professor.
Was it? Can I ask you if it was enough clear?
Yes.
Yes.
Okay. So all the mathematical details. I mean, this is, really the take-home message. If you want to tell someone what's grasping control. Grasping control is apply forces to an object that has no motor inside, of course. You want to use a robot. You need to understand which force you want to apply. You compute the contact forces with the grasp matrix, and then you go back from the contact forces to the torques that you need to apply by using the Jacobian transpose. Okay? Both Jacobian transpose and grasp matrix have the complexity of vectorial product. If you look to the mathematics that is inside these two matrices is just vectorial product, because you go from forces to moments and you need the vectorial product with an arc. That's the complexity, no more, okay? Now, I'm going to leave, we take 5 minutes rest, and I'm going to give the stage to Maria Pozzi. Maria Pozzi is a postdoc in my research lab. She contributed to the research in grasping control and design since years. I'm very happy and honored to have Maria in my team, and she developed with me and other colleagues this toolbox. This toolbox has been founded directly by MATLAB. So we started, so we had a huge experience in grasping. We developed this toolbox, and MATLAB at a certain point decided to give us money to develop that course based on our toolbox that has been, if I remember well, downloaded 8,000 times or 10,000 times, Maria? 10,000 times, and this used by many research center all over the world, from NASA to DLR Center and many others. Okay, let's take 5 minutes and we go further with the singles.
Thank you, Professor. And if we have some questions from the participants, if there is any questions from the participants, in between, can we take a screenshot also? So may I request Professor to stop the sharing of the screen so that I can take a screenshot?
We take a screen picture?
Request the participants to turn on their video.
Okay. I will share the screen.
You can just stop sharing the screen. Yeah.
So, Vijay, you take once this picture where Professor is seen at the center, and then you can take a grid view as well.
You need to pin me. You need to pin me.
Yeah.
Yeah, I will pin you.
Yes. So take more than one so we can take the best.
Yes, sure.
Joking.
Just a minute.
It's a digital selfie.
Yeah, I've taken one and then.
Grid view नहीं ले रहे हो विजय?
Yeah, I'm
Grid
taking
view?
grid
Okay.
view also. I have to take 2 grid view because multiple participants are there. So I'm just taking that also.
Great. It's like I'm smiling since 5 minutes. So it's, it's like a paresis of the. No, joking. I mean, we cannot joke with this kind of disease. Not at all.
No.
Sorry for that.
Okay, we have to keep smiling actually for our own health.
No, thank you.
That adds to augmentation. Some kind of augmentation is needed.
Yes.
Thank you very much, everyone. I've taken the screenshots. Thank you.
Okay, so
Professor Domenico, this is Professor Shamanta Hazarika. I would love to put on record the help that Maria Pozzi had extended in potential grasp robustness codes to my PhD student, Hirak Basumatari, if she remembers, Maria.
I didn't fully understand what you said, sorry.
You had helped my student Hirak Basumatari with potential grasp robustness codes.
Ah, great. Okay, yes.
Yeah, and we have acknowledged you in the paper.
Great.
Wonderful.
Thanks. Thank you. Wonderful. Great.
Nice to know that. I mean,
yes, you know, the world is small. I like it. Very
I was
well.
exactly thinking the same. World is becoming smaller and smaller. These.
Yes, I did not expect Maria to be here, and I see her now.
So nice to meet you in person, more or less in virtual person.
Okay. So I don't know. We are almost ready. If we want, we can also consider the 5 minutes break already gone. No?
Yeah, we'll take 5 minutes break. You can resume at 4:09.
Okay.
4:09 Indian Standard Time. Thank you.
Okay. See you in 5 minutes. Okay.
Yeah. So
Good.
after 5 minutes.
I will be here, but you will
Yeah.
see speaking. I mean, I will say ciao at the end of the lecture of Maria. Okay. Good. See you in
Okay.
5 minutes.
So I think we can.
Yes, we are here.
Yes, sure.
Yeah.
Maria?
So thanks, Maria, for sparing your time, and then you will be presenting us the MATLAB programming for this. Thank you very much.
Thank you for hosting me in this course. So I will start by with a few slides introducing what SceneGrasp is, and so I will share my screen.
And may I request those who are already having their MATLAB on their laptop, desktop, if they can also go, I mean, they can also do practice simultaneously. That would be great.
Yes, actually, I will show a few slides, and then at the end, I will show how to download and install SceneGrasp, so that then we can do some exercises together.
Okay, that's great.
Right. So please feel free to stop me if there are questions, if there is something you don't understand, because this should be quite interactive part of the lecture. Okay, yeah. So I guess now you can see my screen.
Yeah, and we can see your screen.
Okay, so I'm going to present this MATLAB toolbox for grasp modeling and simulation that we call the SceneGrasp. Basically, the motivation behind the birth of SceneGrasp was that our group was studying grasping and in general robotic and human grasping, and so we needed to have tools to simulate and analyze grasps in an easy way and in quite intuitive way, also to visualize grasps. You will see that SceneGrasp has several functions also for visualization. So that's why we decided to start developing SceneGrasp. I say we, but actually SceneGrasp started in 2012, and actually I was still at my bachelor, so I was not yet in the lab. So it started even before me entering in the robotics lab. But I started working with SceneGrasp since my bachelor thesis, so it's been quite a while. And so SceneGrasp was born as a MATLAB toolbox for the analysis of grasping, in particular with underactuated and compliant hands. I'm not sure whether you already talked about these topics, but actually you can have different kinds of robotic hands. And typically, I mean, the most simple, let's say, case is when you have a hand that is built of fingers, and each finger has joints, and each joint is actuated by a motor. Okay, so you have one motor per joint, basically. So those are fully actuated hands. Then there are hands in which joints are coupled, and either physically or just from the control point of view. And then those are underactuated hands, and the underactuation could be in the design of the hand or or could be used to control multiple degrees of freedom. And about compliance, you can model the hand joints by thinking that there is a sort of virtual spring between the joints, simulating the fact that the hand might be compliant or even made of compliant materials, or for example using elastic joints, for example. So that's what we mean by underactuation and compliance in a very short way. So of course here you can have a deeper look in previous papers to see the details, also the mathematical details. Anyway, SceneGrasp was born for simulating hands that are fully actuated or underactuated with compliance. And the main features of SceneGrasp are that it has a graphical user interface and a scripting interface. Actually, the graphical user interface is quite intuitive to use because you can place a hand and an object in the space and then plan a grasp. But of course, the scripting one is more versatile, and you can really write down and define the models that you want to use. That's why we'll focus on the scripting part. Then it is possible, as I was saying, to model hands and objects, and so to build the models, to place the models in the space, and if we want, we can add to the hand model the synergies, the under actuation. This is the first time I talk about synergies, but as you might have already understood, the scene, the initial part of scene grasp, of the name scene grasp, comes from synergies. What are synergies? Synergies are ways in which humans actually control their hand. So basically, when we grasp things, we do not think about moving each joint of the hand alone, in each of them separately, but we actually perform patterns of motions, okay? And this was discovered by neuroscientists, and it was applied in robotics to simplify the control of multi-fingered hands. So instead of specifying a goal position for each of the joints of the hand, and here we have, for example, an anthropomorphic hand with 20 degrees of freedom. So instead of specifying what each joint has to do, we can specify a pattern and of closure, and the hand can perform it directly, not controlling joint per joint. So it's just one control input instead of 20. So again, here I'm explaining it very quickly. Of course, there are several papers, and if you want, we can give you the references about synergies. That is a concept that was born, was discovered in neuroscientific studies, and then was applied to robotic hands, to the control of robotic hands. So actually in scene grasp, it's possible to define synergy matrices and synergies for hands of different types. Once we have defined the hand and the object, we can define a grasp by defining contact points. So here you will see that either we can apply, we can define the contact points manually, like suppose we have already achieved a real grasp with a real robotic hand, and we want just to analyze that grasp. So what we can do is to transfer the contact points on our hand model in scene grasp, and then start to analyze it. For example, we can compute the grasp matrix, the J matrix, the H matrix that is about the contact models. We can evaluate the compliance, and so on and so forth. So for an analysis purpose. Instead, if we want to plan grasps with scene grasp, what we have to do is to define a hand, an object, and then close the hand over the object in different ways, and we will see some details on this, and decide and pick the optimal grasp according to a certain measure. So to define a grasp, we have these two ways of doing it. And then again, for grasp, if we want to do the grasp analysis and not the synthesis as in the grasp planner, we have several functions that can help us. So let's go into the details of a few aspects of scene grasp. So concerning the hand modeling, we have already several hand models included in scene grasp. You will see that there is an anthropomorphic hand like the one you see here that is called paradigmatic hand. Then we have, for example, the Allegro hand and other commercially available hands. Or there is, for example, this modular hand that is actually a very simple gripper with 3 fingers, and each finger has 3 modules, and all the modules are the same. And to actually define a new hand, what we can do is to write down its Denavit-Artenberg parameters. So I'm not sure whether you are familiar or not with this. So if you have questions, please let me know, or if you need references, let us know. But basically, Dynamic-Tatenberg parameters are a systematic way of computing the direct kinematics of a manipulator. Okay, so if you think of these robotic hands, and this is probably what you already saw also with the professor. So each finger of the robotic hand can be seen as a robotic arm, okay, made of a sequence of links that are the rigid parts, the phalanges of the fingers, and joints that actually allow the motion between fingers, between the links. So Dynamic-Tatenberg parameters is a standard way to describe the structure of a manipulator, and then to compute and this helps in computing the direct kinematics. So basically, to define a hand, we need to specify the Dynamic-Tatenberg parameters of the fingers. And this is something that is typically available if you buy a commercial hand, or I mean, it can be available, or at least you have the way to actually derive the parameters from the specification of the hand. Otherwise, if you build your own hand, of course, you have to write down the full Dynamic-Tatenberg table, okay? Here you see an example of a code in which we are defining a hand. So we just have to type hand equal and then call the model that we want to load. Now here we are loading the left Allegro hand, and we can specify a T matrix that is an homogeneous matrix that describes the pose of the hand in the workspace. So T is an homogeneous matrix, meaning that it's a 4x4 matrix containing a rotation matrix and a position vector. The rotation expresses the rotation of the reference frame of the hand with respect to the world, let's say, and the position says where the center of the hand is placed in the workspace. Okay. Then, as you can see here, as I was telling you before, it is very easy to plot hands and objects in SceneGrasp. So you can just use this function sgplot, okay, sgplot hand or object, and then give as input the hand or the object you want to plot, and you have it on your figure, okay. Then we will go in the code. So this is just to show you a first idea, and then we will just write it together, okay. So concerning objects, we can define objects with primitive shapes. For example, I mean, a sphere, a cylinder, a cuboid, and we have special functions that do this. For example, here we see an application of the function sgsphere. That is a function that defines a sphere based on what? Based on H, that is again an homogeneous transformation containing the rotation and the position of the hand, of the object. Then we have, for example, to specify the radius. In the cylinder, we have to specify the radius and the height. Okay, so each shape has its attributes. And then we can specify also, for example, the plot resolution. So again, once we have defined the sphere, we can plot it very easily. Now we are in the process of studying even, I mean, it is also possible to import custom objects from STL files. And this function is still not available in SceneGrasp, but we are working on making it available. Then concerning the grasp definition, so we have defined the hand, we have defined the object, now we have to define the grasp. As I was telling you, we have two ways of defining a grasp. If we want to analyze a grasp that has already been, let's say, obtained, for example, in a simulation or in a real case, we can take our hand, put it in a certain configuration, and then add contact points through these two functions, SG at contact and SG at the fingertip contact. Basically, they are the same, but SG at the fingertip contact is built over the other one and actually adds contact directly to the fingertips. Okay, the other one can be used also to add contacts in other parts of the hand, like the other phalanges. And then I'm not sure whether you see my hand. Yes. Okay. So sorry, I was checking. Then the other way to define a grasp is to use the grasp planner. So in general, when we talk about grasp planning or grasp synthesis, typically this is defined as the problem of finding the best contact points over between the object and the hand to grasp the object in a good way or optimal way with respect to a certain quality measure. Okay, so the grasp planner in SynGrasp is a quasi-static grasp planner, so it doesn't take into account the inertia properties of the hand or of the object for the moment, but it computes different grasps between a hand and an object, searching for the best grasp, okay, according to a certain measure. How is it done? Basically, the hand is moved around the object and then closed from different positions over the object to find the best contact points. And contact points are detected in a geometric way. So basically, we are searching for the intersection between the cylinder constituting the phalanx and the object. Okay. So there is no computation of forces or dynamic properties in the current implementation. It's a quasi-static implementation. Still, we can do some computations in the quasi-static modeling. So in the framework that also the professor was explaining. So to come back to the grasp planner, basically what we have to do is to define some grasp planner parameters that are, this n is the number of different poses around the object that you want to test. And QM type means, I mean, you can call it as you prefer, but this is quality measure type. So the type of quality measure that we want to optimize. In this case, we have the grasp isotropy index. You can find further information on this in the literature and in the toolbox. And then we have to call the grasp planner and give to the grasp planner the hand, the object, the number of attempts, and the type of quality measure that we want to optimize. After that, we can plot the new hand, okay, in the final configuration, and we have this final configuration. Of course, I mean, you will see that it takes a while for the grasp planner to compute the optimal grasp. And why is that? This is because for each iteration, we have, so for each of the poses of the hand with respect to the object, we have to compute the closure of the hand. And at each step of the closure, we have to check whether we reached some contact points. Okay, and for each grasp, then we have to compute the quality measure. So it takes a while. Of course, the lower is this number, the less attempts you do. So you might get not very good grasp, let's say, but the higher is this number, the slower is the computation. So just to summarize a few numbers of SynGrasp. So as I was telling you, this book was developed starting from the 2012 mainly by Monica Malvezzi, Domenico Pratichizzo, Guido Gioioso, Jonathan Salvietti, and later by me. So it's a toolbox that has been developed by our group in Siena, but it is being used in several works. There are more than 300 functions and scripts for grasp analysis. This is the main subject of 3 scientific papers about SINGRASP itself, and this last one is a recently accepted paper on the extension of SINGRASP to include also the dynamic of the grasp. We have more than 10,000 downloads of the toolbox, more than 8,000 downloads of the user guide. So, of course, there is a user guide and there are papers on SINGRASP. So again, if you want to study further the toolbox, you can actually go there and read the guide. It has been used in 5 European projects recently. And the most important thing is that SINGRASP is a toolbox that is continuously growing. Typically based on our research. So whenever we need to add functions, then maybe we do first the paper and then we try to publish the functions online. But of course, in general, we welcome the user's help and suggestions, and you can write to this email or directly to me or the professor if you are interested in developing code and modules for SINGRASP, or while using the toolbox you find errors. So these moments for us in which we use SINGRASP with students are very important because they allow us to test and debug our code. So please whenever you find an error, please let us know, because of course we tested the functions, but maybe they were tested in different MATLAB releases. So it's always good to have feedback on that. Okay, so what you can do now is you can go to a browser and search for SINGRASP. I'm not sure whether do you have questions? I cannot read.
Any questions from participants? Anyone?
Okay. So
Maria, can you see me?
Yes.
I don't know if people can see me, because you were talking about we were talking about the quality of the grasp. Okay, so I want just to show a quick. I don't know if you can pin my face.
Yes, Professor, I am pinning you. Yeah.
Okay. So the main idea is this one. So from mathematics, it will be clear that the closest you are to barycenter, the better is for the grasp quality. Now, this will be clear. So if you're far from the basis, suppose that this bottle is full of water, the barycenter is in the middle, okay? Then the best way to grasp this bottle is to take the contact points around the barycenter, because it's more difficult to destroy the contact constraints, okay? To break the contact constraints during the motion, okay? So basically, if the water is still the middle of the bottle, so it's better to grasp here, or to grasp here, or it depends on the water. So choosing the contact points is one of the main part of the grasping strategies, and it means that there is a sort of AI, a simulator behind, then try to do the test and picks the right contact points, because we are doing it with our biological intelligence. The computer needs mathematics, and for example, being close to the barycenter is an intuitive interpretation of the quality of the grasp. Just Maria, I wanted to quickly give an hint about what it means to choose the contact points. Sorry to interrupt.
Okay, no, thank you. It was great. So now, I mean, those of you that have MATLAB already and can go in a browser and search for SINGRASP. Actually, the first website that appears should be this one, and this is the SINGRASP website. Then, at least to me, there is this. It appears this link that is actually the course that we developed, you know, the course that also the professor was talking about, developed also thanks to the MATLAB contribution. So here you can see there are also video lectures about grasping, so you can actually navigate a bit the website if you want. But this is another story, so let's go to SingGrasp, and in the download page, you can see the latest release of SingGrasp and you can download it. I will do this operation with you so you can follow me, okay? If you have questions, please let me know. So you can just copy paste SingGrasp in a folder that you want. You have to extract it. Okay. And then
the process is not visible.
What is not visible?
The process, what we are supposed to do with MATLAB?
No. So first of all, you have to download the folder from the website. So okay. I'm not sure whether you saw the website. So if
no,
I
we
mean,
didn't.
I can give you the link in the chat. But anyway, if you search for SingGrasp in a browser, you will for sure find it. Let me just send you the link.
You can put it in the chat box.
Here, the chat. Yeah.
So it is in the chat box.
Okay. So from there, you can download the SingGrasp 2.3. That is the latest release. And once you have downloaded it, you can put it in a folder that you prefer. I put it in my folder for today's exercises, okay? But you can, you know, put it wherever you want, okay? Then, if you go in MATLAB, you can go just here, your folder, open your folder in MATLAB. So open the folder where you have SingGrasp in MATLAB. I will just wait a few seconds. Okay, and once you are here, you can actually run this SG install. Hopefully you see my screen well, I'm not sure. But basically in the folder of SingGrasp, there is this SG install.m that you can run. And then in theory, okay, all the functions are added to your path. I mean, there are other ways to install SingGrasp. It's just a toolbox in MATLAB, so you can just add your path, the folder where SingGrasp is to your path. Okay, because SingGrasp is just a set of functions. Okay, it's not something you have. I mean, you only have to include its path in the MATLAB path. Okay, so what this script does, it's actually that. It's nothing else. Anyone that couldn't download SingGrasp?
SingGrasp 2.3, right?
Yes. Unfortunately, I cannot see you all. So, can you raise your hand if you downloaded the SingGrasp? Okay. Okay, not sure whether there's any. Okay, great. At least once, that's perfect. 3, 2. Okay, great. So then now you have to try to install it. And great. So many of you are already downloading it. So can you raise your hand if you already installed SingGrasp? Okay. To test that everything went smoothly, you can just write here and equal SG paradigmatic. Okay. And in theory, you should find this answer. Okay. So if you have problems in the installation, please let me know. Otherwise, I will go slowly ahead. Okay. Okay. So what we can do.
I have some issues when while installing it, ma'am.
Say again?
Ma'am, I have some problem while installing it, ma'am. I have downloaded, but I cannot. I don't have any options to install it, ma'am.
No. So once you have downloaded it, you have to open the folder in MATLAB. Okay.
Oh, okay, ma'am. I should open it in MATLAB. Okay, ma'am.
Okay. Okay. So yes, you have to open your folder in MATLAB. So you go in MATLAB and you select the SingGrasp folder, let's say, here.
Yes, ma'am. Sorry, ma'am, but I don't have MATLAB, ma'am. I will install it later and try it, ma'am.
Okay, okay. So anyway, so later, okay, you will try. So I will just keep going. Basically, once you have your folder open, you can just run the script that is sg install, and then it should install the toolbox. Okay, so if we go ahead, so suppose we want to write down a script with SingGrasp. What we can do is to start and no, wait, let me just show you this the toolbox because it's more important. No. Okay, here it is. So the toolbox is made of several folders, okay? And the most important ones are the following. First, there are the examples. So here you can find some examples on the various, using hands, using grippers, or examples related to papers, okay? For example, this is an example related to a paper. Again, also this one, also this one. These are the very basic examples, and I will actually show you a modification of this one. Okay. Then another important folder is the modeling folder. In the modeling folder, we have, for example, all the sample hands, which are the hand models. Okay, so these are the hand models that are already included in SingGrasp. Whenever you want to define another hand model, you can just go and copy paste the structure of the models that you see here. And after that, you can actually modify the parameters, the DH parameters according to your model. I will show you in a second what I mean by that. And then you have other folders, for example, the one containing different quality measures that compute the measure, so given us a grasp, compute how good that grasp is according to different criteria. and yeah, so on. I mean, you can actually freely explore all the toolbox. Let me show you an example of a hand. So the nice thing of SceneGrasp is that we are trying to have very clear helps for the functions, okay? So each function, for example, this is a function that defines the Allegro hand model. So this function, you see, has the contributors, so those who worked on that. Then you have some references, so meaning works in which those functions were used, articles, okay? Then you have how you can use the function and what you have to expect, okay? So, and each function in SceneGrasp has this type of help. And if you find problems with the help part of the functions, please let us know. So, this is the hand model of the Allegro hand. For example, the Allegro hand is a commercial hand with 4 fingers and 4 joints per finger. Based on the data sheet of the hand, we derived the parameters of the hand, and the most important thing is that for each finger you have to define the DH parameters of the finger that are basically a matrix of values describing the structure of the finger, okay? That's it. I mean, inside the Navitar parameters, you have angles and distances describing the kinematics of the model. So when you have your own hand, you can just go in and just substitute the parameters of your hand inside these tables. Then at the end, you see there is this block that is equal for each for all hand models, actually this block, okay, in which all the DH parameters are put together to form, of each finger are put together to form a finger and then to form a hand, okay. A hand in SceneGrasp is nothing but a structure, okay, with several fields. So here I define this paradigmatic hand, for example, the anthropomorphic hand. So you can see here that you have different fields. The first one is the field containing the structure of the fingers. So each finger is a structure and is associated to the structure of the hand. Then you have the number of fingers, the number of joints, the position, the actual configuration of the hand, the configuration of the fingers, and several other things. You will see that here you have the hand Jacobian that becomes populated once we define some contact points, because as the professor was telling you, the hand Jacobian and the grasp matrix are the most important matrices in grasping. And then you have other matrices, and we are not going to talk about them, but these are, for example, the stiffness matrices of the hand. Okay, and then you can call your hand in some way, and that could be useful in different applications. Okay, so if we go to an example, okay, let's. Can you see my screen? I mean, can you see the writings? Do you need a bigger font?
It is fine.
Okay, thanks. So, for example, suppose you want to use the Allegro hand, okay? So, the first thing that you can do is to call the function that models the Allegro hand, saying hand equal to SG Allegro something. That could be right or left, okay, SG Allegro left in this case. And as we saw in the slides, you can specify a pose of the hand. So an orientation of the hand in the space and a position of the hand in the space, okay? So there might be cases like this one, for example, in which you have to do that because, for example, in this case, we wanted to check, since so if you want to use the outputs of SceneGrasp with the real hand, you have to be sure that the reference frame that you're using in SceneGrasp is the same as the one used in the control of the real hand, for example, in ROS. Okay, so this is a nice function to be sure that, to ensure that we always have the model of the hand oriented and positioned as the one in particularly oriented as the one we are using maybe for control, okay, for example. But you can have different reasons for doing that. So let us arrive here. So if I plot hand, okay, here you see that we have a hand with 4 fingers, and the Allegro hand has 4 fingers. It's a real robotic hand. We have it also in the lab here in Siena. It has 16 joints. So as a result, the Q vector describing the configuration of the hand has 16 components. As the professor was saying, in grasping, it is very important. I mean, all the mathematics behind the grasping is the algebra of matrices and vectors. So it is very important to know and to be sure that the sides of vectors and matrices that we are using are coherent with what we are doing. Okay. So, and of course, why is that a problem? Above all, because when we have to multiply vectors and matrices or matrices with matrices, we always have to be sure that the sides of the matrices are correct. Okay, otherwise we cannot perform the multiplication. I will not go into the details because I think you already know this, but it was to tell you again. Okay, then what did I do here? So I defined the hand. If you want, you can even write it down if you have SceneGrasp open. I'm going slowly because of that, so that if you want, you can write it. And then, for example, here we extracted this vector of values for the joints. We extracted it directly from the real hand. So when you have the real hand in a home position, okay, you can read the joint values, and if you want, you can put it in SceneGrasp, create a vector, and then move the hand in that position. Okay, so at the moment our hand is in this configuration, is in the configuration 0, 0, 0, 0, 0, 0, 0. Okay, so the hand is fully stretched. When we move the hand with this instruction, and we didn't yet execute the instruction, you will see that the hand will change position. Okay, so to repeat, now the hand configuration is this one, all the zeros, and you can see it by plotting n.q. Now here I put transpose just to have the row vector. Okay, if we go ahead and we do one step, so we move the hand, okay. No, sorry, we have to go one step more because, okay, here. Now the configuration changed, and actually we assigned the home configuration that we computed, for example, from the real hand to the model. Okay, so this function is quite important in SceneGrasp because it moves, it assigns to the hand a new configuration. An important thing in SceneGrasp, and you have to be sure to remember this, is that whenever you want to change a hand and then be sure and then ensure that the results of that change are imported in your original hand, you always have to say hand, so your model equal to a certain function that takes into account as input again hand. Okay, so to be sure that the changes are reflected onto your original model, you have to always do this assignment. Okay, not just to call the function, because if you just call the function, nothing changes. Okay, not like this, but like this. And then we can just plot the function, the hand. Okay, and here it is. Okay, so this is the Allegro hand in a home position that we decided. If you want, we can even run again the script without moving the hand. Let me just. Okay, and here you see that when the hand is not moved, it is fully stretched. Okay, all the joints are 0. All the joint values are 0. So all the joint positions are 0. Okay. This hand has joints that allow the closure of the fingers, and also the rotation of the fingers around their axis, for example. Anyway, this is what we get when the hand is not moved. And then if we move the hand by using SG move hand, we get the hand closed. So I'm going quite slowly, even though these are functions that are they are doing quite simple things, but these are very important. And above all, you can you have to remember, I mean, these important functions. Okay. Another thing that we were saying before is that let's suppose that we want to define a grasp. So suppose we have this real hand that grasps an object, and we know where the contact points are, and we want to analyze this grasp. So if we want, we can just let's say grasp definition. Okay. What we can do is to use the function SG add contact, but suppose we don't know how it works. So we go here, we say help SG add contact, and grasp tells us what does this function do. Okay, so the usage is the following. Let's copy paste it, and then we talk about it. So we have several arguments that are taken from the function SG add contact. Let's see them. So first of all, it's the hand. Okay, great. Our hand, we have to add it's the hand on which we have to add the contact points. Then we have to say the type of contact point. What does type mean? I'm not sure whether you already saw it or not. If not, it's not it's not fundamental that you perfectly know these things now. But just to tell you, is there anyone wanting to say something?
Yes, Maria, we only saw the model with friction.
Okay,
I think that at this stage, we can just stay with that one. And we can just say that there are other models, but the model with the contact with friction is the most popular one. Exactly. So basically, in general, you can have the different contact models to model the way in which the forces applied at the contacts, forces and torques, are transmitted to the object. The most used model in grasping theory. Say it again.
Ma'am, is it that the force of the contact is being depends upon the object, or is being coded by us, ma'am?
No, sorry, I didn't understand.
Ma'am, we are having some grasping power. Like we need to have some force to take the objects. Like, ma'am, if you are taking a liter bottle, means we need some force to grasp it. Is this the same force is being applied to the all, or it's been censored? But it depends upon the weight of the object, ma'am.
No, so the amount of forces that you have to apply depends on which forces you have to counteract. So if you have to counteract the gravity of the object, you have to apply enough forces to counteract the gravity, but as the professor was saying, also enough forces to stay in the friction cone. Okay, this is a slightly different thing I'm talking about here. So we are talking about modeling, and basically there are several contact models. With SynGrasp, we have these 3 contact models, okay? And you can select the contact model when you are defining a grasp. Here, we will only use the first contact model, that is the hard finger. That is the contact model that the professor was using, meaning we only consider forces applied at the contacts, and we consider also the friction cone, okay? So this is just to tell you that it exists. Now we don't go into the details of the contact models at the moment. So basically you can choose the contact model. So we'll put 1, okay? It's also to show you that SynGrasp has very nice help parts, okay? So the help tells you everything that you have to know about the function. Then you have to select the finger in which you have, in which you want the contact point to lie, okay? This see where, and let's start with the first finger. And then you can choose the link on which the contact point goes. Let's do. And then there is this alpha parameter that tells you in which point. So when you define the link, you define the phalanx, and then to define inside the phalanx where the contact is, you can put 1, and then the contact will be at the end of the phalanx, or 0, and the contact will be at the beginning of the phalanx, or 0.5, and the contact will be in the middle of the phalanx. Okay, so if you put alpha. So let's see if it works. Okay, we don't see anything on the hand yet. We didn't plot the contacts, but if you go and see hand.cp, we can see that we have 1 contact point. This is the position of the contact point, and these are the parameters of the contact point, exactly those that we were discussing before. Okay, so the hand structure now has a field CP containing all the contact points. In this case, it's just 1, but what we can do is to do something like for we can add the contact to all the fingers. Okay, for example, in this way. Okay, why? Because I'm iterating over I. In this parameter here is the see where, so it's where the thing in which finger the contact should be, and I'm iterating from 1 to hand.n, which is the number of fingers of the hand. Okay, so if I run this thing, you will see that we have now 4 contact points. Okay. Okay. Then what we can do is, first of all, we can compute. No, not yet. No, because we have to. Okay. Wait a second. So what we can do now is to define an object. So what we can do is the following. So we can plot the hand. Let's see how it comes, because the position is not great. Sorry, it's object. Okay, so now it's a bit strange because the position was not exactly for a grasp. Maybe it was for a grasp of a large object, kind of. Okay, but so what happens with this function that is sgplotObject is that we define the function automatically defines an object based on the contact points. So we have defined the contact points, okay, here, and we have defined the contact points on the fourth phalanx. That is actually the last phalanx. It's the fourth because we have a dummy phalanx at the we have one dummy phalanx at the base of the finger, but okay, never mind. So here you have the so you have the contact points, okay, in the middle of the fourth phalanx, which is the last phalanx. Even if you see 3 phalanges, actually there are 4 because there is a dummy phalanx, as I was saying. And basically, this function sgMakeObject actually, draws an object, a virtual object actually, between all the contact points. This virtual object is, however, useful, first of all, to see whether we placed the contacts in the right ways, in the right points, okay? And it's okay because we wanted it to be in the middle of the last phalanx, okay? Then it's nice because it allows us to do some grasp analysis. Why? Because once you define this object, actually, you also define a full structure of an object, of the object, including the G matrix. Okay. So we have object.g, that is the G matrix, and hand.j, that is the hand Jacobian. Okay. I think you saw with the professor that the G matrix has this structure, identity, and then above, under it, it has the skew matrices. Okay. So if we look at the sides, I told you it's very important to know the sides. So the sides of the grasp matrix is always if we are in a 3D case, and if it's not, there are not strange cases, we have 6 by the number of contacts times 3. Okay, so these are, we have 4 contacts times 3, that is due to the contact model, and it's 12. Whereas the hand Jacobian is always number of contacts times 3, so if we are applying the hard finger contact model. And in this case, we are applying the hard finger contact model, so it is okay that we have 4/3, and then times the number of joints of the hand, 16, because the hand has 16 joints. So again, it's possible that now it seems a bit confusing to you. So if you have questions, please let me know. But I am sure that once you have you put together all the notes from the lecture and what you are saying here, it will be clearer. Okay. Okay, so I can show you one last thing. And actually, I invite you to navigate in the toolbox and run the examples and see the functions. Because, for example, there is also a function to plot the contacts. It's SG plot contact, if I remember well. Contact. No, I don't remember it. I don't remember the exact name. Contact points. So SG plot contact points. For example, if you want to visualize and be sure that your contact points are well defined, you can add, you can write, you can use this function. Okay. And as you can see here, for example, in the graphics part, you have different kinds of graphics that you can plot. Anyway, so let me go back to our exercise. So as we said, so in the first thing that we saw, we actually defined some contact points on the hand, and we let's say we computed the grasp matrix and the G matrix according to that. But we defined the contact points manually, as you know, we wrote add contact point. Now we can check what happens if we want to actually plan a grasp, so to the grasp synthesis. What we have to do is to define again a hand, an object. So here we have, for example, the sphere, but you could have a cube or a cylinder, okay? And we define the position of the sphere, for example, and so on and so forth. And what we can do is to plot the hand and the object in the initial position and plot the end of the object in the final position after we have run the grasp planner. Again, as I was telling you before, the grasp planner takes the hand, the object, the number of attempts you want to do to find the best grasp, and the type of quality metrics, to quality measure, okay, for the grasp. So if we run this script, as you can see, it takes a while because we are using the grasp planner, and as I was telling you, it has to try several different configurations. Of course, there are ways to make these computations more, faster. It's you can optimize the code, of course, with respect to what we wrote here. So what you get is this. Sorry, but due to the I cannot move the finger. Due to the interface of Zoom, I cannot really move the figures. Oh, here it is. Okay, so we have the initial position configuration of the hand open over the object, okay? And then we have the final configuration in which the hand is wrapped around the object. Okay. And this was computed automatically by our grasp planner. How? According to the index that we told the grasp planner to optimize. And then the grasp planner gives as output the final hand, which has a certain matrix of contacts, and also the final object, which actually is the same as before. And then, but so the object is the same because it's still the sphere, but the structure of the object changed because now we have a G matrix coming from the contact point matrix. Okay, so the object is always the same, but the structure describing the object now is changed because we have a grasp. And then we have an index, the index of quality. Okay. Of course, you can get better results if you do more attempts. Okay, I think that's more or less this from this more practical part. Please, if there is anyone that already tried, please let me know. Otherwise, I mean, if you have comments and questions later on, maybe you can let us know. But I mean, these are the basic functions of SingGrasp, and we will give you an exercise exactly doing the same things that we did today, but with an anthropomorphic hand, which is the paradigmatic hand. So the idea is that you will have these exercises, but I will. I think the professor will send you. And basically we have, okay, wait a second. No, okay. I changed a bit the exercises I sent you, so don't send them yet. But anyway, so basically I will ask you to, use the anthropomorphic hand model, move it in a certain configuration, define contact points over the hand, and then use the SingGrasp grasp planner to plan a grasp with the hand. Okay, so the both approaches. Remember that also this anthropomorphic hand has a dummy phalanx at the joint at the first at the beginning of the finger. So the first phalanx is a dummy phalanx, and this is due to the fact that here we have two joints at the finger, at the base of the finger, one doing this motion and one doing this motion, but these two joints are in the same place, so the distance between them is 0. Okay, so there is a kind of dummy phalanx in that. But I think by looking at what we did today and looking at, above all, at the examples in the SingGrasp toolbox, you will be able to actually do these exercises. Okay, if there are no comments on this, I will proceed to the final, very final slides. I see there is something in this chat. Okay, oh great, there is someone that was able to install. Thanks for letting me know. Hopefully you also followed a bit what I was saying. Okay, very last thing about SingGrasp and say its applications. I will show you a very recent application of SingGrasp. So many of the papers in our lab were powered by SingGrasp in the sense that we used SingGrasp to achieve simulation results before using real robots or to test control strategies and so on and so forth. Because SingGrasp is very important for research, but also for education, as we are doing today. One of the latest works in which we are using SingGrasp is the one in which we added the possibility of the dynamic simulation of the hand. This is a paper that was recently accepted in Frontiers in Robotics and AI. And basically what we did was to connect SIMGRASP and Simulink, so still staying in the MATLAB framework, by writing some functions that, using the programmatic model editing, that is a way to edit and create Simulink models automatically. So these functions, using this programmatic model editing, allow to automatically generate not only the SIMGRASP hand model, but also its corresponding model in Simscape, in Simulink. And so this is nice because we don't have to, sorry, there is a bit of noise here. So this is nice because we don't have to actually, build each hand model in Simulink by putting there directly the single blocks and so on and so forth. But we just need to, we can do it using scripting language, so using MATLAB scripts, not using the graphical user interface. And this makes the work much faster. And then, of course, if we want to modify some parameters or some blocks, we can even use the graphical user interface. And the nice thing of going towards a Simulink is that we can use Simscape, which is the mechanical simulator, dynamic simulator within SIMGRASP that is capable of simulating the physics of bodies, okay, of objects, of different objects. And with Simscape, we can actually simulate the grasp dynamics, the contact detection, and perform grasp control strategies. For the moment, we released some functions that are available at this link. Soon they will be also in the main SIMGRASP website that we saw together. These are examples of applications of experiments that we performed with the simulator. Here you see the anthropomorphic hand that we saw just a second ago into the previous slides, just at the beginning of the lecture. Here is the same exact hand, but in Simscape. So here we are also simulating the fact that the hand has a mass. So each finger of the hand has a mass and there's a certain shape and so on. And we want to, as a future work, we want to also implement not only rigid materials, but also compliant materials. Here you see a video of the working principle of the simulator. Here, for example, we are showing the contact detection. So here we detect a contact in the second phalanx. Okay, and what happens? So this was the contact in the second phalanx. Then we detect a contact also, sorry, in the first one. Not sure it's fully synchronized. Yes, more or less. Okay. Then we detect a contact with the last one, and then we detect a contact with the palm, and also the last phalanx. Okay. So here you see that we have these graphs showing that at the end we have all the phalanges in contact. Here are other examples of grasps. You see that, for example, so even here, the object is wrapped around by the hand, and also here. Okay. So our future work include the inclusions of other standard object databases, the simulation, so inclusion of functions for the simulation of soft robots, other educational resources, and also the implementation of, I mean, a few functions that allow the control to control the hand in synchronous directly with ROS. I mean, we did it already for a few works, but we didn't yet, you know, release the functions. Thank you very much for your attention. I don't know if there are questions. We have 4 minutes for the questions. Thank you for your comments.
Thank you, ma'am.
Thank you, Maria. Participants, if you have any questions, just ask.
Hi, I have one question regarding SynGraph. So regarding the deformable object manipulation, is there any update regarding, will there be any update regarding deformable object manipulation, or can you suggest ways to utilize SynGraph to evaluate them?
So for the moment, we are not, I mean, we don't have functions included in SynGraph that handle deformable objects. We have, so we will, we are now working on simulating deformable parts in the hands. So like the gripper I was showing you a second ago with the pink phalanges that are actually made of deformable material, and I mean we will also try to use similar approach to simulate deformable objects. Of course, also there it depends on how much deformable they are and how much we want to be accurate in the simulation of their dynamics. So I mean, but we start first with the hands and then go to the objects.
Okay, thank you, ma'am.
Thank you.
No more questions. So thank you, Mari.
Thank you again for hosting me.
Yeah. So,
thank you very much.
Thank you. I don't know if the prof wants to say goodbye, but yeah.
I think Professor busy with something.
Yeah, probably yes.
Ma'am, I have a question.
Okay.
So this mechanisms also, no?
Sorry, I cannot really hear you. Can you repeat or write?
Just repeat it. Your connection is poor, so it is better you write in the chat box.
Mechanisms. Okay. So the toolbox as it is now, in the toolbox as it is now, you can simulate compliance at the joints as if there were like, you know, virtual springs at the joints, okay, through the matrix KQ. We are now working towards instead having not only the quasi-static modeling of the compliance that is already available, but also the simulation of compliant materials like the one I was showing before with the you know with flexible links. So we can use flexible material, the simulation of flexible material within Simscape to simulate parts that are flexible and compliant. But this is very it's not even in the accepted paper, this part. So it's something we started developing really very recently. And instead, what is already available there is the quasi-static modeling of the K, which in some cases it's enough to have some preliminary results. So it really depends on what you want to achieve with the simulation. Thank you for the questions.
Okay.
Okay, so I actually tried to work to the professor, but I'm not sure.
Yes, I'm here.
Okay.
Yeah,
Okay.
Professor is here.
Okay, so thanks, Maria, for this nice introduction of Synchra. And what I can say see you tomorrow at same time, same place.
Yes, thank you.
Bye-bye.
Bye-bye. Thank you.
So
Bye.
thank you all. Thanks all the participants. Thanks Professor Domenico Pretichiuso and Maria for such a wonderful session. We're really enjoying it. And I hope that all the participants have benefited. The question answer session itself is telling. Thank you so very much. Have a great day, all of you.
You too.
Bye-bye.
Bye-bye.
Bye.
Thank you, ma'am.
Thank you, ma'am. Thank you, everyone.
So I am ending the meeting now. And tomorrow, same time, we will start. 2 o'clock Indian time.